This lecture is an overview of symmetric block ciphers, which are widely used today. We will talk about the basics and then look at Feistel cipher structure and the inner workings of two block cipher standards, namely Data Encryption Standard, which is also known as DES, and Advanced Encryption Standard, which is also known as AES. So block ciphers, as the name says, process data into blocks. So what we do is we divide our plaintext or ciphertext into blocks, each block being the same length, and then we encrypt or decrypt each block individually. We can use block ciphers to process any kind of data. This could be text, this could be images, this could be audio, and so on. And if the last block length is not equal to that of the previous block, then we add padding, right? Because we always want to make sure all blocks are of the same length. So typically today in block ciphers, we use a 128-bit block. And so in block ciphers, we use both substitution and permutation together, right? These are the two basic operations that we talked about earlier when we looked at traditional symmetric encryption techniques. So we talked about substitution ciphers and we talked about transposition ciphers. And we perform substitution and permutation a certain number of times to create what is known as an SP network. And the idea here is to create more confusion as well as add more diffusion to make cryptanalysis hard. Right, so confusion is mainly added through the use of substitution steps, whereas diffusion is usually added through the use of permutation steps in order to hide patterns. Now, there are many block ciphers available today, but the two most popular ones, which have been used as standards for quite some time now, are DES and then AES, which is the current standard. But if you just Google, you will find a lot of different block ciphers. We have twofish, we have blowfish, GOST, Camellia, and so on. So this brings us to a question, which is that does a stream cipher provide confusion or diffusion, or does it provide both? Well, a stream cipher only produces confusion because technically it is only doing substitution. There is no transposition or permutation. And if you remember, stream cipher encryption and decryption is just an XOR operation, right? If I have 1000 as my plaintext and my key is, let's say, all ones, if I encrypt them together, then I have 0 and I have all ones, right? So you can see here the input bits and the output bits are not the same. Whereas if we are doing permutation, then input and output bits are usually the same. So there is no permutation step here, but there is substitution, right? So 1 is substituted with 0 here, then 0 is substituted by 1, and so on. Here are some parameters that are important for block cipher design. Now, every block cipher needs a block size, it needs a key size, it needs rounds, a round function, and then round key generation algorithm. Now, block size defines how the data will be divided for processing. As I just mentioned, blocks have the same size, so we usually pad the last block to make it the same size as the other blocks. And today, we typically use 128-bit blocks with AES, but the standard before, which was DES, used a smaller block size of 64 bits. Then each block cipher works on a specific key size, right? Again, today the minimum required key size for symmetric ciphers is 128 bits. So AES supports that minimum key size. However, DES had a smaller key size of 56 bits, because of which it was prone to brute force attack. Later, it was sort of made more secure against brute force attack by performing triple DES, which sort of expands the key size from 56 bits to 112 bits and 168 bits. AES, on the other hand, also supports larger key sizes of 192 bits and 256 bits. Each block cipher also has a certain number of rounds, which defines how many times we are going to repeat a set of operations, namely substitution and permutation. Each round has this round function, which consists of the substitution and permutation steps, as well as how to incorporate the round key. Right, so block ciphers take a symmetric key as input and they expand this key into multiple keys, one for each round. Therefore, each block cipher has a round key generation algorithm as well. But this is not the same as pseudorandom number generator, because typically over here we just need around 10 to 16 keys, because we have around 10 to 16 rounds usually. Now, many modern symmetric block ciphers such as DES, blowfish, twofish, and GOST are based on Feistel Cipher Structure. So it is important to understand how it works before looking at other block ciphers and their encryption and decryption process. So this structure was proposed by Horst Feistel at IBM in 1973 and first commercially seen in IBM's Cipher Cipher, which was designed the same year. So the nice thing about this structure is, as you can see in this figure right here, that the encryption and decryption process is exactly the same. So this technically looks like a copy and paste of one figure. This is the encryption process, this is the decryption process. And if you notice, there is just one slight difference in the encryption and decryption process, that is that the keys in the decryption process are used in reverse. So in encryption, we have keys starting from 0, 1, all the way to n, but in decryption, we just reverse the order of the keys. So we start with kn, then key n-1, and then all the way down to key number 0. Everything else stays the same. So let's look at how this structure actually works. So let's look at the encryption process first. So since this is a block cipher structure, so the first thing you would do is to take the plaintext and split it into blocks. All of the blocks have to be equal size. Then you take individual blocks and then encrypt them individually using this Feistel Cipher Structure. Right, so you take a block and then you split it further into two halves, two equal halves, the left half and the right half, as you can see here. Right, so let's say if I have a 128-bit block, then I would split it into a 64-bit left half and a 64-bit right half. Then what we do is we process the right half using the round function along with the round key. So again, since it's a block cipher and we have certain number of rounds, and for each round we need to have a round key. Right, so you can see over here, we take the right half and then we process it using this round function. And this round function could have multiple types of substitution steps, multiple types of permutation steps, right? So this f just generalizes what will happen inside this round function, okay? And so we also need a round key. So this is the round key that we are passing into this round function, okay? And whatever the output is after we process the right half using the round key and using this round function, we basically XOR it with the left half. Now notice that for XOR to happen, you need to have equal size on its left and right side, right? So basically here, if we are again talking about a 128-bit block, Then the left half is going to be 64 bits, and again, the output of this round function is also going to be 64 bits. So we XOR them together. Okay, and after that, we actually do a swapping operation. So whatever the output is after this XOR, we take that, and that becomes the right half for the next round. Okay, and then we take the right half from this current round as is, unprocessed, and then that becomes the left half for the next round. Okay, so notice here again in this round we still have a 128-bit block. Let's assume that we are dealing with 128-bit blocks, and this again is going to be 64-bit left half, and this is going to be a 64-bit right half. Okay, and then we just keep repeating this process for n rounds. So this n basically is going to be specific to a block cipher. So for example, for DES, which we will take a look in a while, has 16 rounds. So n is equal to 16, which also means we will need to have 16 round keys. Okay, so again, here the right half goes to the round function along with the round key. This is a different key from the previous round. Okay, and all these round keys are generated from that single symmetric shared key between the sender and receiver. Again, the output of the round function is going to be XORed with the left half. And again, this output is going to go and become the right half for the next round. And the current right half for this round is going to become the left half for the next round, and so on. Now, the only thing to keep in mind is that after you process the last round, right, once you have the output of the XOR, you don't do the swapping, right? So whatever the output is, that becomes the left half, and then that last round's right half unprocessed becomes the output right half. And this basically becomes our ciphertext block. So left half concatenated with right half, right? So the result of the last round is the ciphertext block. And then you repeat this whole process again for all the other plaintext blocks. Now pause here and try to encrypt the following plaintext using Feistel Cipher Structure. So here you have some information. For example, the plaintext is 1A in hexadecimal, which basically is 0001 1010. So it's 8 bits. Okay, and then assume that we have block size equal to 8 bits. Okay, basically that means that once you split this plain text into blocks, you just have one block of 8 bits. And then assume that we have 3 rounds, and then in each round, this is our round function, which basically means that we are going to do a substitution, and then we're going to do a permutation. So first what we do is we take the right half and perform the AND logic operation with the round key, and the output of that is going to be permuted. So what we do is we do a circular left shift by 1 bit on that. And that is going to be the output from here. Okay, and then again, that output is going to be XORed with the left half, and then you do the swapping. Okay, and then I've also provided the round keys here. Since we have 3 rounds, we have 3 round keys. So try to complete this exercise. So let's try to encrypt the plaintext 1A, which is equal to 0001 1010. Okay, so the first thing to do is that we split this plaintext into blocks. So we just actually have one block because the block size is 8 bits. So our block is actually 0001 1010. Okay, now we had 3 rounds. We're going to process this block into 3 rounds using the round function. which was doing one substitution and one permutation. Okay, so let's take a look. So let's first look at what is our left and right half. Right, so since we have 8 bits here, we'll take first 4 bits as the left half and the next 4 bits as the right half. So basically 0, 0, 0, 1 is the left half, 1, 0, 1, 0 is the right half. Okay, so we take our right half and we pass it through the round function and also give it the round key, which let's call it round 1 key. So the first round key was 0, 0, 0, 1. Okay, and then what we're going to do is we're going to process this round key and the right half using the round function. So if you remember, we had 2 steps, the substitution, which was just doing AND logic with the right half and the round key. So we have right half 1, 0, 1, 0, and our key is 0, 0, 0, 1. So if we do the AND operation, which basically just means that only if the 2 bits, corresponding 2 bits are 1, you have a 1 as the output, otherwise you always have a 0. So since we don't have 2 corresponding bits as 1 in any of these cases, we will just put all of them as 0. Right, so that's the result of the AND operation of the right half with the round key, and that's our substitution. So after that, what we do is we do the permutation, which is just a circular left shift, but because all of these are zeros, even if you do a circular left shift by 1 bit, they're still going to be all zeros. What this means is that the output of this round function is all zeros. So now what we do is we XOR this output with the left half. Now XORing 0, 0, 0, 1 with 0, 0, 0, 0 is going to give you 0, 0, 0, 1. Right, so this output is 0, 0, 0, 1. Now what we did after that, this is round 1. What we did after that is swapping. Right, so this one is going to come here. Okay, so we will have 0, 0, 0, 1 here. As the new right half. Okay, and then the right half of this previous round as is becomes the new left half. So we will have 1, 0, 1, 0 here. So again, we repeat the same thing. This goes through the round function. The right half goes through the round function. This is the right half, this is the left half. And then we provide it the round key. So now the round 2 key is 1, 0, 0, 0. Okay, and so let's process the right half with the round key using the AND operation. Right, so we have 0, 0, 0, 1 as the right half, and the key is 1, 0, 0, 0, and we do an AND operation. Again, none of these corresponding bits are ones, right? So these two, 1 and 0, is going to give us 0, 0, 0 is going to give us 0, 0, 0, going to give us 0, 0, 1, going to give us 0 also. And again, doing a left shift on this output is again going to give us all zeros. So once again, actually we have all zeros as the output. Then we do exclusive OR of this output of round function with the left half. And since we have all zeros here, doing exclusive OR with 1010 is going to give us 1010. So again, what we do is this was round 2. Okay, we do swapping. So this comes here. We have 1010 as the new right half, and then the right half of previous round, which is 0001, as this comes here. Now this is the new left half, this is the new right half, and we are in the last round, which is round 3. Okay, now again the right half goes through round function, and we have our round 3 key, which is all ones. Okay, now again let's do the processing. We have a right half, which is 1010, and round key is 1111, and then we do an AND operation on these. Now we have corresponding bits as 1 in this case, so we put a 1, then 0 and 1 gives us 0, 1 and 1 gives us 1, 0 and 1 gives us 0. Okay, output of that is going to be circularly left shifted by 1 bit, which means that this first bit is going to go towards the end, right? Everything is going to move left. So we will have 0, 1, 0, and then 1. Okay, so output of the round function actually is 0, 1, 0, 1, and then we do an XOR of this output with the left half. Okay, so we have 0 and 0, which is 0, and 0 and 1, which is 1, 0 and 0, which is 0, and 1 and 1, which is also 0. Right, and then the right half of this round is 1010. Now remember, after the last round, we don't do any swapping. So whatever is the output of this XOR operation of the output of round function with the left half, this becomes our left half, which is, and the right half is the right half unprocessed of this current round, which is 1010. So this becomes our ciphertext. So basically our ciphertext is 0100 and 1010, which actually is 4 and A. So let's look at the decryption process. As you can see here, it's pretty much the same as the encryption process, but the only difference is that the keys are used in reverse. Right, so again, just like the encryption process, first step is always to break the ciphertext into blocks of equal size. So again, if we have 128-bit blocks as the block size, we will take our ciphertext and split our ciphertext data into equal blocks, each one having 128 bits. And if the last block does not have 128 bits, we will actually pad it. And then we take individual blocks and process them using this structure. And then we take each block and perform this decryption process on it. So each block is going to be split into 2 equal halves, left and right, just like the encryption process. Right, and then we process the right half using the round function, just like we did in the encryption process. Nothing is going to be done in reverse. So the same type of substitution and permutation are going to be performed in the same manner in this round function. Right, so we take our right half, process it using the same substitution and permutation steps that we did in the encryption process. And then we also need the round key. But in this case, we're going to use the last key, the last round key as our first round key, right? So kn is going to be used in the first round. And then we take the output of the round function, XOR it with the left half, just like we did in the encryption process. Right, and then we do the swapping this output comes here and becomes the new right half, and the right half from the previous round unprocessed becomes the new round's left half. Okay, and then we repeat this for n number of rounds, and after the last round we don't do any swapping, right? So once you do the XOR operation, the output is the left half, in this case left half of the plain text because we're decrypting, and then the right half of this last round unprocessed becomes the right half of the plain text block. Right, and then we repeat that for all the ciphertext block. Now again, what we'll try to do here is try to decrypt the ciphertext that we got from the previous exercise and see if we're actually able to find the plain text, which was 1A, using this ciphertext 4A. So pause here and try to complete this exercise and try to decrypt this ciphertext 4A. Again, all the information remains the same as we had for the encryption process. The only difference is that now you're going to use these keys in reverse, right? So you're going to use key 2 first, key 1 then as the next key, and then in the end you're going to use key 0. So let's try to solve this. Again, our ciphertext is 4A, which basically means it's 0, 1, 0, 0, 1, 0, 1, 0. Okay, so that's 8 bits. And we have to split our ciphertext into 8-bit blocks. And this means that we just have one ciphertext block, which is 0, 1, 0, 0, 1, 0, 1, 0. And then this is our left half of this block. This is our right half of this block. So let's process this block in 3 rounds. So we have 0, 1, 0, 0, 1, 0, 1, 0, left half and the right half. So we take the right half, pass it through the round function, and use 1, 1, 1, 1 as the first round key, which is actually the last round key for encryption. Okay, and so what we do inside the round function is the same. We will take the right half and the round key and do an AND operation first, which is our substitution step. Okay, so again, this will give us 1, 0, 1, 0, and then we do a left shift on the circular left shift. This will give us 0, 1, 0, 1. This bit will go here. Right, so we'll have 1 at the end. Okay, so we'll put this as the output of the round function, 0, 1, 0, 1. And then we XOR this with the left half. This gives us 0, 0, 0, and 1. Okay, so then we swap these. This becomes the new round's right half. And the right half, as is for the previous round, comes here. We have 1, 0, 1, 0. This is round 1. And then we're doing round 2 now. Okay, so again, this will process through the round function along with the round key, which now is going to be 1, 0, 0, 0. Okay, so let's do that. So take our right half, this one, and do an AND operation with the round key. 0, 0, 0, 0, and left shift is also going to give us all zeros. So we can have all zeros here. Now this one XORed with the left half will give us 1, 0, 1, 0. Again, we do a swapping. Right, 1, 0, 1, 0 will come here, and then the right half as is will come here. So right half is this one, so 0, 0, 0, 1 will come here. And now we're doing round 3. Again, we take right half, pass it through the round function, and the round key now is 10001. Again, the same substitution and permutation steps. 10100001. We do an AND operation. 0001. Oh, 0, sorry. And then left shift, also going to give us all zeros.